Okay, so I'll start with the discussion of the problems right now. I hope you can see my screen. Please let me know if it's not. And also if I'm in between, if I'm less audible or something, if my volume goes down, please let me know. Right. So, there's my screen. Oh, sorry. Yeah. So coming to the first problem, it's essentially the problem is to help you understand and get used to the process of differentiation. So talking about differentiation, it is essentially a relation between two variables, how one variable changes with respect to the other. So in this, let's say we have dx by dt, then we are talking about how x changes with t, right, where x and t are two variables here. So here f of x represents f of x is essentially you would take it as a graph where on the x-axis you have the variable x and on the y-axis you are plotting the f of x function. So from the scenario, from the picture of a graph, let's say you have something like this. So at any given point of x, x naught, let's say, so at this point the dx by dt would be the slope of the graph at that particular point. Dx by dt at x naught would be the slope of the at that particular point. So basically the differentiation is to find out the slope of a function in this scenario, right? So if we look at the first problem, first bit here, we have f of x equal to 233. So here 233 is a number, it's a constant. So as such, the graph would look like something like this constant 233, which is f of x, and this is x. So when it's constant, d by dx of f of x would be 0, since this is a constant and there's nothing inside to differentiate with, which is a function of x or something changing with x. Nothing is changing with respect to x since it's a constant, so we have the slope or the differential of this f of x as 0. Coming to the next bit, we have f of x equals 2x square minus x, right? So here if you see d by dx of f of x would be again 2 times the differential of x square. So here the rule which we use is d by dx of x power n is given by n into x power n minus 1. So here that would correspond to 2 times. So x, this is x power 2. So the differential of x power 2 would be 2 into x power n minus 1, that is 2 minus 1, which is 1, minus differential of x, again with the same rule, you have x power 1, so 1 times x power 0. So this would be 4x minus 1, right? So the rule we used is d by dx of x power n is equal to n into x power n minus 1. So the thing with differentiations is that one, you have to know a certain number of basic to get more used to it, to know you have to know certain number of basic rules, which you the first time you it would help if you can derive from the first principles, that is dx by dt. You could write as f of uh, x plus t minus f of x plus t minus f of x whole divided by delta t, or the t change in time. That is how the differential is defined as change within or different change in x with respect to change in t, right? So from that first principle, taking limits that the change in time is tending to zero, if you can you can derive for the few of the basic rules, and then you get a better understanding of differentiation. Then you can perform that for certain basic functions, and then remember those as rules. Your life will become easier in solving more differentials. So one such rule is this n into x per n. So the next bit we have is f of x equals e power x plus 1. So again, if somewhere I have also by mistake taken some wrong question or something, also please let me know. You can point it out. Okay, so we have e power x plus 1. So d by dx of e power x plus 1. That's what we need to do, which would be. So how can we write e power x plus 1? 1 is e power x into e, right? So e again here is a constant. So d by dx of e power x into e. This would be e into d by dx of e power x, since e is a constant. So again, this is the other rule which we'll be using here, that is differential of an exponential, that is e power x is again e power x. So we have e into e power x again, which is equal to e power x plus 1. Right. So yeah, rule used is d by dx of power x equal to e power x. Coming to the next bit, we have f of x equal to x into 1 minus x by k. Right, yeah. So how do we write this? You can write this as x minus x square by k, right? Just here taking the x inside the brackets. Now we take the differential of this d by dx of f of x. Here would be d by dx of x minus d by dx of x square by k, which would be here for d by dx of x, as we have seen before, it's in the first bit. This second bit, it's 1 minus d by dx of x square by k. Again here k is a constant, so it would be 1 by k into x square. So 1 by k is a constant here, so you would bring it out, 1 by k times d by dx of x square. So as we had again seen in the bit b, differential of x square is 2x, so into 2x, so which would be 1 minus 2x by k, right? So the rules here we used are the same, just that the form of f of x we expanded it to suit the process of differentiation we are using. Uh, the next with the f of x given for the e bit is kx by 1 plus x, right? So the rule here we'll be using here, rule using here would be d by dx of, let's say you have two different functions, f of x by g of x. Then you can write this as f dash of x, that is f dash of x is or f prime of x is essentially again d by dx of f of x, that's just a shorthand notation, into g of x minus f of x into g dash of x or g prime of x, the whole divided by g of x whole square, right? So what would that be for this particular function in our case? D by dx of f of x would be f prime of x, that is d by dx of kx times 1 plus x minus kx times d by dx of 1 plus x, the whole divided by 1 plus x whole square, which would then give d by dx of kx. Again, k is a constant, so you can get it outside the differential. You have k times d by dx of x. Again, as we have seen in the bits b and d, it's just 1, so k times 1 into 1 plus x, which is g of x, minus k times x times differential of 1 plus x. So differential of 1 is again I wrote 0, yeah, 0. So differential of 1, which is a constant, is again 0. So you have the 0 plus again differential of x, which is 1, right? The whole divided by 1 plus x whole square, which would be k into 1 plus x minus kx by 1 plus x whole square, which would be k by 1 plus x whole square, since plus kx and minus kx would get cancelled, right? This is with the first question, which is essentially differentiations. So if you have any doubts in these or in the concept of differentiation, you can ask me now. I'll just wait for a minute. Alright, then we'll move on to the second question, which is essentially integrations. So integration is in the form of graphical sense, if you see. So if we have x and f of x and some graph. So the second one, say the second question is essentially indefinite integrals. We do not have limits to the integration. But the third question is definite integrals. We have limits to the integration. That is, we have from one x1 to x2 you do integrate. So essentially what you're doing is you're trying to find out the area. In indefinite integrals, you're trying to find out the area from minus infinity to infinity, but just that because that would be some other value, you have a general you have a equation for that particular area in terms of x itself. So that is what indefinite integrals looks like. So the first question, we'll solve the indefinite integrals. So the bit a, we have integral of x square minus x plus 1 dx. Also, integrals is kind of, if you think about it, opposite of the differentiations. So they are kind of inverse functions. So if I take this function f of x and then I do d by dx of f of x, you'd get some differential of it. Now if I take the integration of this with respect to x, if I take this as some new g of x function and then I do integral of g of x dx, what I would get is f of x. So this is a relation between integration and differentiation. So here for the first bit we have integral of x square minus x plus 1. So again, as in the previous case, we can break it down into three separate integrals here. So that would be integral of x square dx, and this dx term here is very important because that is the variable with respect to which you are integrating. Suppose let's say there was some other variable y which is independent of x, and that would have been y dx, and y is independent of x, then this would be y integral 1 dx. You can just consider that as a constant and bring it out if y is not depending on a. So that would so essentially that's what you need to remember. So this dx is it does matter. You cannot forget that if the function inside here is not in a function of x, the integral loses its meaning in a sense, right? So let me just erase this. Yeah. So x square dx minus integral x dx plus integral 1 dx. Now here we'll be using the rule integral of x power n dx. So rule we'll be using here is used integral x power n dx would be x power n plus 1 by n plus 1, right? So coming to the first integral x square dx, that would be x cube by 4 x cube by 3 minus x square by 2 plus x by 1 plus a constant c which we add so as to tell that the integral will have certain meaning, in the sense that to have different, if you come to definite integrals, you wouldn't have to put this constant here, since you know from the limits from which you're from which and to where you're integrating. But in indefinite integrals you do not have that, and that's the reason you add this constant here to remind that. And we have, so x cube by 3 minus x square by 2 plus x plus c as your answer to the integral here. So the next bit here would be integral of kx by 1 plus x dx, right? So for this, so integration sometimes it's not as straightforward as differentiations. You would have to do some, use some innovative techniques, or small changes to the equation, so that you make convert it into forms which are easier to integrate. So in that sense, here we make a substitution. So we take another variable u, which is equal to 1 plus x. So du would still be equal to dx. So since d1 dx of 1 would be 0, since 1 is a constant, d by dx of 1 would be 0, and then for x it would be dx. And substituting that into this equation, we would have integral of k into u minus 1 by u du, right? So that would be, so again k is a constant, so you can always bring it out of the integral. So it would be k integral 1 minus 1 by u du, so which would then be k times integral du minus integral 1 by u du, should be k into u minus ln of u, ln of mod u, plus some constant. I mean, both integrals would have a constant, but you can always write two constants together as a single constant. So again, the rules which we used here would be rule used here would be integral of 1 by x dx is equal to ln of mod x plus c, of course, right? So the integral would then be k times u, if you get k inside, you have k times 1 plus x minus k, a natural log of 1 plus x plus c, right? So this is the answer for the b bit. Now going on to the c, we have integral of k by x dx. It's exactly the same rule which we have used before. So again, bring k out of the integral, k integral 1 by x dx, which we have. So as we have seen in the rule here, so that would be k times ln mod x plus a constancy, right? So the next integral would be d integral of k times e power minus ax dx. So that would be k, bringing it out again, since it's a constant, e power minus ax dx. So here another substitution which we would like to do is, we can do is take a new variable u, which is equal to au, and then that would imply that du is equal to a into dx. Since a is a constant, it just comes out of the differential, right? I think I just made a mistake here. This is ax. Yeah. So now substituting this into the integral, we have the integral as k times integral e power minus u a into du. A is a constant, again it will go out, so we have a k integral e power minus u du. Actually we could have we could take u equal to minus ax instead, so that would make our life more simpler. Then this would just be e power u, and we have minus a here, minus a times du. So we have minus ak as a constant outside times e power u into integral of e power u du. So again, integral of e power exponential function e power x dx, the rule which we will be using here is e power x. Rule used, integral e power x dx is equal to e power x. So that would give us minus a k e power u, right? So that would be minus a k e power minus ax, of course plus a constant. I'm really sorry about it. I think I made a mistake again here. So du would be minus 1 by a. Since this a would be coming this way, we'll have dx equal to minus 1 by a du. Sorry about that. So we'll essentially have instead of minus 8, it's minus 1 by a. So minus k by a. That's the solution, right? So next, the fifth bit, we have integral of 1 by x into k plus x dx. Okay, so here what we need to do is the problem here is that in the denominator we have two terms of two multiples, in the sense that we have x into k plus x, and we do not know how to differentiate, how to integrate this particular form. So what we try to do is break this down into two different fractions. So this is something called partial fraction. So where the form, the thing, how you write this as 1 by x into k plus x is what you have. So you try to write this in form of a by x plus b by k plus x. Okay, this for the first order ones. So here you have x and k plus x in first order. So you essentially, there, if you add two fractions like this, the denominator would be exactly the same thing, and numerators we'll have to find out what they are, right? So we have a times k plus x plus b times x as the numerator, which is equal to 1. So we have ak as a constant plus x into a plus b equal to 1. So for this to be 1, we need a plus b to be uh, 0. So we have a equals minus b, we can derive from this. And then we have a k equals to 1, which would imply a equal to 1 by k, which would then imply b would be equal to minus 1 by k. So we can write this fraction 1 by x into k plus x is equal to 1 by k times 1 by x minus 1 by k times 1 by k plus x. Now we'll integrate this particular function. So the integral would be integral of this would be integral right. So that would turn out to be 1 by k is a constant, so we can get it out. 1 by k times integral of 1 by x dx. Again 1 by k, you bring it out. Integral of 1 by k plus x dx. For the first one, it's straightforward. We have 1 by k times ln mod x plus a constant minus 1 by k times. So for this, again what we do is we substitute as similar to as substitution we had seen here, u equal to 1 plus x. Here it's the same substitution, just that instead of 1 it's k, another constant. So you can write it as integral of 1 by u du, where u would be equal to k plus x, right? So which would then be 1 by k times ln mod x plus c minus 1 by k times ln mod u plus another constant. We can completely we can write this together as 1 by k. I take common, so that would be ln mod x. I'll write constants to the end, so minus ln mod k plus x plus a particular, let's say this one was c1 and c2. We could write the whole together constant as c3, right? Yeah, so this should be a solution for the last bit. Right, so this with the second part. Let me know if you have any doubts in this. Not, I'll move on to the third. So in the third, we are doing the same integrations, just that we are doing the definite integrals. So we have the first one, integral 1 to 3 e power x dx. So again, we'll do the integral independent of the limits and then put in the limits in the end. So we have this integral of e power x dx, as previously we had seen, was e power x, right? So here we have integral of e power x dx is e power x. We do not have a constant, since the constant would get cancelled anyways. If you, let's say, plus let's just write constant for the first one, plus we take a constant and we write 1 and 3, that would be equal to e power 3 plus c minus e power 1 minus c. So we would have e power 3 minus e power 1, so something around 2.7 whole cube minus 2.7 should approximately be something around 17 something, right? This is something so you need to note down. So definite integrals, you do not need to consider the constant, you can just take the limits directly, uh, integral limits. So for the next bit, we have integral of 1 to 4 x square plus 2x minus 5 dx. Then that would be equal to integral 1 to 4 x square dx plus integral 1 to 4 2x dx minus integral 1 to 4 5 dx. Can as in the previous second question we had seen, integral of x power n dx is equal to x power n plus 1 divided by n plus 1, right? So here that would be x cube by 3, but limits ranging from 1 to 4, plus 2 into x square by 2, limits ranging from 1 to 4, minus 5 times x ranging from 1 to 4, right? So then we have 4 cube 64 by 3 minus 1 by 3 plus 2 times square 8 minus 1 by 2 minus 5 into 4 minus 1, right? That would be equal to 21 plus 15 minus 15. So the answer would be 21, right? Coming to the C bit, we have integral 0 to 2 x by 1 plus x square dx, x by 1 plus x square dx. So here again we use our substitution method. So here we put u equal to 1 plus x square, a new variable. So again we have du equal to 2 into x dx. So x dx is something we can write here. X dx would be equal to 1 by 2 du. Substituting this into our integral, we have integral 0 to 2 half du divided by u. So that would be 1 by 2, taking the constant out, 0 to 2 1 by u du. So integral of 1 by u du, as we had seen previously, is a natural log of ln u, a natural log of mod u. So here anyways the constant would be cancelled, so we'll directly take limits from 0 to u 2. So strictly speaking, the limits I have written here are not correct, since the limits also change as the variables change. So I would have to write this as something else. So since we have taken u equal to 1 plus x square, I'll just write it in a different color. So if x equal to 2 implies u would be equal to uh, 5, and x is equal to 0 would imply u equal to 1. So this would mean these limits would have to change from 0 to 2 to 1 to 5, right? To 5. Alternatively, you can just have them as 0 to 2, but then you have to convert in the final step, this step you have to convert the variable which is written here in u into x, and then u, and then solve this definite integral. That is to say, either you have to solve it in this way, or you have to write half of ln mod 1 plus x square and then write the limits from 0 to 2. So you'll have to write it in either way. So solving it, we would get half of ln 5 minus ln 1. So ln 1 would be 0. So we'll have half of natural log 5 natural log 5, and then this you would have to solve this natural log using calculator, and then find out the exact value. right? I'll leave it at that. And then we have we go to the next bit. We have integral of integral 1 to 2 x cube dx. So again we use the rule of integral x power n dx is equal to x power n plus 1 by n plus 1. So that would be, in this case, we have x power 4 by 4, limiting from 1 to 2. We have 2 power 4 by 4, which is 4, minus 1 by 4 should be 3.75, right? Next, the fifth bit, we have integral 0 to 2 x times 1 minus x times 1 minus x by 2 dx. So again, to solve this, we can just expand it with inside the integral to x minus x square by 2 dx. So this would be integral 0 to 2x dx minus integral 0 to 2 x square by 2 dx. So which would be equal to x square by 2 from 0 to 2, and then since 1 by 2 is a constant, we take it out, and then we have x square inside the integral, so this would be x cube by 3 from 0 to 2, which would be equal to 2 minus 0 minus half times 8 by 3 minus 0. That will be 2 minus 4 by 3 is equal to 2 by 3, which is 0.67. Right. So these are with the differentiation and integration questions. If there are any doubts, I'll just wait for 1 minute. Please let me know. Else we will continue with the rest of the problems. All right. Just to check, I am still audible, right? Uh, Maybe someone can leave a message in the chat if I am audible. You're still following? Yeah. Thank you very much. Okay. So going on to the fourth question. So what they asked us to do in this question is to identify the linear or non-linear systems of ODEs. So the first bit we have, so this all of these bits here given are systems of two variables, that is to say two state variables, as dx by dt equals ky by 2, ky minus 2, and dy by dt. We have two variables, x and y, dependent variables essentially here. So dy by dt equals x minus y minus b y square. So now, is this linear or non-linear? That is the question. So the difference is that in linear, so the right side of these equations, the of this difference, the dx by dt and dy by dt are on the LHS. On the RHS, you on the right hand side, you need to have all the powers of the variables, dependent variables x or y, to be only first order. So there for it to be linear, that is to say, it has to be only x power 1 or y power 1. It cannot be x power n or y power n with n greater than 1, or x power n into y power n, y power m, where n or m is greater than 1 or greater than 0. So essentially there is no xy term, or there is no x square or y square or higher order terms for it to be linear. So what would you say the first one is? So since there is a y square term here, it would be non-linear. For the next bit, we have dA by dt equal to PA minus QB, and dB by dt equal to QB minus RA. Here we have only terms in first power, so a power 1 or b power 1, and there's no a b term or a into b term as well. So this system here would be linear since there are no higher order terms on the RHS, right? And C, we have dp by dx equal to 1 minus 2pq. dq by dx is equal to p minus 0.2q. There's no problem with this particular dq by dx since on the right hand side p is power 1 and q is power 1. But on the first one here we have a pq term, so that would make the system non-linear. So this is non-linear. The system whole as a whole becomes non-linear. In D we have dp by dx equals 1 minus 2p, and dq by dx equals p minus e power q. So this is another form of non-linearity. So the first one is linear, 1 minus 2p, there is no higher order terms of p. And the second we have p power minus e power q. So this is another form of non-linearity. If to look at it as the non-linearity described before, higher order terms of q or something, you can take the uh, power series of e power q, that is the expansion of e power q. You would have something like p plus p square by 2 factorial plus p cube by 2 factorial. You'll have q square by 2 factorial plus q cube by 3 factorial and so on. That is, you'll have all the powers of q from right from 0 to infinity. So this would be a non-linear term. Right. So that is with the fourth one. Coming to the fifth question, they've asked us to identify the second order and nonlinear ODEs. So they have given us two things to do. One, to see to confirm that it's nonlinear, and the other also that it should be second order. So what does that mean? The second order term here corresponds to the LHS part. It could as well be on the RHS, but you generally, when you're writing the equation, you bring the dx by dt or d square x by dt, all the terms to the LHS and the rest to the RHS for our purposes here. So we have a dx by dt equals kx minus b. So this is looking at the RHS, we see that it's only x power 1, so this is linear. And on the LHS, we see that it's dx by dt. That's the differential is it's only a first order differential. That is to say, it is this is a first order, not a higher order. B, we have d square x by dt square, which is equal to sine of x plus x. So this is definitely second order, since LHS we have d square x by dt square, and then since on the RHS we have sine x, which is again a non-linear term, we have non-linearity in system as well. So this is non-linear. C, we have y double dash, which is double prime, which is again, as I said, it's a form of writing the differential. So this is same as d square y by dt or whichever other variable you're using, which would be equal to 2y square plus y minus 1. I'm assuming that y is a function of t, that's why I've written dt square in the bottom. It could as well be any other variable. So this again on the LHS, if you see, it is a second order term differential, so it is second order. And then on the RHS you have a y square term, making it non-linear. Y square, so y is raised to the power 2, so no, not linear anymore. Coming to D, we have d square x by dt square equal to rx minus kx. So this, if you see LHS, it is definitely second order, but then on the RHS, if you see, x is not raised to power more than 1, it's only x power 1 everywhere, so it is linear, right? So the answer to our question, the identify second order nonlinear ODEs, would be B and C, right? Next, sixth question. They have given us a graph here of y versus x, or something like this, right? um, Now they've asked us to the solution of one of the ODEs below is plotted here. Identify the correct ODE. So they have given us three differential ODEs, which is dy by dx equal to 2 plus y, b dy by dx equals 1 plus y square, dy by dx equals y power 4. Okay, so one brute, this is a graph of y power x. So one brute force method would definitely be to, solve all the three integrals on the right RHS, a, b, and c, and then plot the function over. But that is not an advisable method since it's just it'll just take time. Uh, Another thing you can do is use your computer or a plotter on the you can find many plotters on the website where you can just plot these equations to then find out the curve exactly. So another deduction method which you can use here is that here we have a graph of y power x. So what dy by dx at any given point is slope of the graph, as we had seen before, right? Slope of the graph. So if you see here at this point, slope is in this way, that is positive. Till here, it is going down. The slope is falling, slope is still positive, but it has decreased. It is moved in this fashion. But coming to this point again, the slope is increasing. That is, it has turned in this fashion. So slope initially decreases and then increases. Also, it doesn't go to 0 at any time. It is positive. It is decreasing at this point, but it's not going flat or that is to 0. It is just decreasing and then increasing. So the three equations A, B, C here are essentially equations giving us the slope of the graph. So which of these functions here behaves in this fashion, decreasing and then increasing, but not going to 0 at any point? So the first one, if you see 2 plus y, 2 plus y is essentially linear monotonous graph. That means it is something like this or this. So it is essentially a straight line. So there is no decreasing or increasing. It's always increasing, right? And coming to 1 plus y square or 1 plus y power 4, they have graphs that are decreasing and increasing. So either y square or y power 4, you have something like this, a parabola kind of y for y square. Similarly for y power 4, but of higher order in this fashion. So what we are plotting here is not y, uh, not y, but dy by dx separately. We take this as a g of x and then we are plotting that, right? So just to look at it, so we have these y power y 1 plus y square and y power 4 showing this behavior of initially decreasing and then increasing slope. But then we also have this condition that doesn't go to 0 at any point, but y power 4 at x equal to 0 is 0. The slope is from this equation is 0, but here we see that the slope is non-zero. So I mean, from elimination and deduction we can say that the answer is B, but then you would have to uh, it's not a method which you it's just deduction method. It's not something, a technical method which you can use anywhere. As such, you would have to plot these graphs somewhere to just check the graphs. You plot it on an online software or anywhere, or you can integrate if you can, and then use those uh, integral shapes again. You plot them on a graph and then compare. So this also you get used to once you try do a lot of plot a lot of graphs, do a lot of integration differentiation. You kind of know the basic shapes of these characteristic polynomials like y square or some quadratic equation, cubic equation, fourth power equations. You know the basic shapes for it, and then you can try to guess these kind of things more easily, right? Next, um, coming to the seventh question, we have the following reversible reaction follows the law of mass action. Find the rate of backward reaction. So we have A plus 2B, K1, K2, P plus Q. So what the law of mass action states is that the rate of reaction is directly proportional to the product of reactants. Since they've asked for backward reaction, reactants here would be P and Q, right? So the rate of reaction would then be minus K2 times P, concentration of P and concentration of Q, since they are directly proportional to those the reactants P and Q, and then K2 as a rate constant of the backward reaction. So this would give you your rate of reaction in the backwards. And since we are taking as a backward sense, we have added a negative sign. If you are looking at the frame of reference of P of Q, you can eliminate negative sign of the K2, but then there would be a negative sign to the forward reaction which he considered here, that is K1, right? That is with the law of mass actions. And then we have the next uh, part, next question 8, which is asking us what are the critical assumptions behind any ODE based biological model. So the first assumption, if you've watched the lectures as well, is that it is a homogeneous system, right? That is to say, let's say you're trying to model a biological cell, then you know that if you let's say you inject a kind of a protein into the cell, then as such speaking, the protein would be concentrated in the area near where you have injected and slowly diffuse over. So when we are considering homogeneous models, we have already considered that it is diffused all over and it has become a homogeneous system completely over the cell. So otherwise our ODEs would not work. So that's why the first assumption we make is that system is homogeneous. This works for the case of diffusions or other components as well. The second assumption is that the size of the system is very large. Or the to say the number of molecules or proteins is very large. Then why do we have this assumption? So let's say we are again looking at a biological cell, and then we have given certain number of, or not any biological cell, given any scenario. Let's say we are trying to look or model the concentration of one particular protein. Let's say there are a limited number of proteins. Let's say there are only 15 proteins. Then it would make a difference if one of the protein or two or three of the proteins are sequestered or sequestered away or degraded. It would make a difference. But just the and the system, the ODE function which we have written, ODE system which we have written, would not be valid for the system anymore, right? It would not be valid for the system anymore. So the assumption, the ODE equations which you have written for the system would fail. So let's say instead of 14 or 15 it was some 14 million, then you remove the same number of proteins or even two orders more number of proteins, it would not make that much of a difference to the system. So the equations which you have written for the system would still remain valid and not fail the system. So these are the two important assumptions you would have to make. You would have to remember very carefully when making a model for the biological system. So I'll just stop for a second. Let me know if you have any doubts. I think we have. Okay. Right. And then if not, then we'll move on to the next question, the ninth one. So the question is that let's make a simplified model of pharmacokinetics. A drug is injected at a constant rate through the IV route. It is metabolized and discarded from the body. So there's an input into the system and an exit from the system being our body. The drug's rate of excretion depends upon the drug's concentration in the body. So we have a degradation term which is dependent upon the variable, that is drug concentration. So we have a first order degradation which would give us minus k, some degradation constant k times x, which is the drug concentration, as the degradation term which is given in the equation, minus kx. And as is already mentioned, the drug is injected at a constant rate. So we take here, I think they've taken the constant rate as a. So we have dx by dt equal to a minus kx as the differential equation defining system. So dx by dt equal to a minus kx. Constant rate of input, first order or rate of degradation. The dynamics of system is represented using the following ODE. Calculate the concentration of the drug in the body after a long time. Imagine we are running the IV delivery for infinite time. X is the concentration of drug, A and K are constants. So what do they mean by after a long time? So for any given system, there is a short-term behavior versus a long-term. Let's say you have a box with a small thermocol balls filled in it. Now you shake it for, or you, let's say just a jar of water you have. You move it around. So now the water is still moving. After you wait for a very long time, the water settles, and that is there is that it settles down, and then it becomes very calm, right? So there's a short term behavior of it being vigorously moving around, and then there's a long term behavior of it settling down completely. So here we are looking at the long term behavior. So what this also helps us do is helps us in accepting the, validating our assumptions. So first being homogeneous. Let's say the drug is being injected through the IV. It would be injected near the arm, or so as such, if you consider the body as a system, it would be concentrated near the arm. But then if you wait for a very long time, it would kind of go over all over the body, and then you can consider, you can imagine it to be a homogeneous system, right? So that assumption is holds, taking it for a long time makes that possible. And also taking it for a long time would mean that the system has reached a steady state. Like the water, it has reached a steady state, that is, it is not changing anymore. There are no perturbations to the system. So here our system consists of the variable x. So when I say there are no perturbations in system, that is, there are no changes in terms of the drug concentration, that is dx by dt goes to 0 at steady state or after very long time. So this is one first method to solve it. The second method would be to directly solve this, integrate and solve this equation by transferring the variables to one side. You have you can take this as integral dx by a minus kx equal to integral dt, and then solve this differential equation using the method we have used in uh, I think the second question, right? Second question, e bit, we had one of the bits, yeah, second question, b bit, we had integral dx by 1 plus x. So this is of the same form. So you can solve it using that. So I'll write it here. Question 2b, same form. You can try solving this. Essentially the constants you would have to take common and put it outside, so that you have in terms of 1 plus kx, 1 plus some constant times x, right? So instead we'll follow this route here of taking dx by dt equal to, goes to 0 at steady states. So what would that be? LHS would be 0. We'll have a minus kx, and directly we have x equal to um, a by k at steady state, or after a very long time. So what you have to understand here is that for the systems we are considering when we write an OD of the ODs, we focus on the steady state behavior of the system to understand what the system finally exists at. So here after a very long time, dx by dt would become zero. That is, there's no variation in the drug after a very long time, and at that time we try to find out what the concentration of drug is, and we have A by K. Right? Is there any doubt in this question or any clarification you would need? Okay, then 10th one, what do we mean by the exact and numerical solutions of an ODE? Exact solution of a ODE would be analytically solving the ODE and then finding out the equation. So that is possible when the ODEs are linear or very some particular nonlinear forms for which it is you have certain methods to solve, techniques to solve. It's not possible always. So you have exact solutions are the ones which uh, uh, analytically solved solutions, right? And numerically solved solutions are always by machine. You solve it, right? Machine or hand or algorithm. Essentially you use an algorithm or a logical steps to solve a particular equation. So that those are numerical methods. And coming to the yeah, this and also numerical solutions would not be the exact solution. You would only hope to achieve an approximate solution, not the correct solution, right? That is something you'd have to keep in mind when solving ODEs. Next, the 11th part, 11th you have, for the following ODE, use the Euler method to calculate the value of x at t equal to 0.3 and consider at t equal to 0 x is equal to 0.1 at t equals 0. That would mean we will take this as some variable x naught or 0, x at time 0 as 0.1. So now the equation we have is dx by dt equal to x by 1 plus x, right? So it should imply dx by dt we write as delta x by delta t, right? And then delta t in the equation they have mentioned we'll be using at 0.1, right? So we have this equals x by 1 plus x. So how do we write delta x? Delta x, let's write it as x of I plus 1 minus I, where I represents the number and x I plus 1 would be the I plus 1th step of the when you're solving. So and given that the equation we can rewrite as I plus 1 minus xi equal to delta t times xi by 1 plus xi, which would imply xi plus 1 equals xi plus delta t into xi by 1 plus xi, right? So what would be x1? X1 would be x naught plus delta t, which is 0.1 times again x naught is given by 0.1, right? 0.1 by 1.1, so which is equal to 0.1 plus 0.1 times 1 by 11, right? What would that be? This would be something around, sorry, yeah, so that would be something around 0.109. Then similarly if you solve, x2 would be x1 plus 0.1 into 0.109 by 1.109, right? That would be, so you would get this to be something around 0.118, and at x3 that that would be which is equal to x at t equal to 0.3, since our time steps are 0.1. That would be x2 plus 0.1 times x2 by 1 plus x2, right? So that would be around 0.128. Okay, this is how you solve using the Euler method. And this is to practice. I would recommend write these in some computer language, so that you can write, you can solve larger equations, and you can try for many other equations. And sometimes this method fails, which is has been explained in the lecture, so you can go through that and look at it exactly. Try solving it. It's fine. You can directly use Microsoft Excel to do these steps as well, which you can watch on the lectures. Professor Bose has explained those, so you can try those at home. For different kinds of functions, so that you get used to it, where the Euler function might work, where it might not work, right? Coming to the next question, we have, how do you calculate the local error in an algorithm for the numerical solution of ODE that uses adaptive time step? So adaptive time step, what you do is, when solving, you check if the current time step is the time step is fine, or it's just your uh, uh, is it giving you an incorrect solution, or versus it's essentially you try to choose a time step value, so that you have some trade-offs between the computational time versus how accurate your solution is. You try to find a balance between these two. Since, let's say, you have this graph, this is the exact solution, and to find the approximate, you at this point you take a slope, and then you try to find out this point, and then so on you go. But then, if you see at this point, in this region, the variation in the function is not that much, so the time step you can take is very large. So you take a large time step from here to here, it doesn't matter. But then when you're here and you're taking a large time step, it matters, because it changes drastically. The slope changes drastically, and you would miss out on the you'd be inaccurate essentially. So at this when the function is changing too much, you would require smaller time steps. But when this function is not changing that much, you can take larger time steps. So what you do is, you have two methods. You can you have two methods. You know which method is more accurate, and then when you're solving, you use the method which you have been using, and then you also solve with the other method, and then check what is the difference between those two. And if there is a small error between those two, and then based on that, you choose the next time step. So that particular error is called this local error. So you have method 1 giving you some estimate x1, and then method 2 would give you an estimate x2. This x2 minus x1 is your local error. So what you do in adaptive time step or designs is that, this local error, you have some and this is, let's say, epsilon. You have some minima and max, min and max. You say that between these two, or if it's there, it's fine. That is their tolerance limit, which you have to define based on your use. So if this e goes beyond max, then what you do is, you change the delta t, the time step, you try to reduce it, so to delta t by 2 or something. If it goes less than min, then you try to increase the time step, so that you can cover, or you can be kind of optimal between the computational time versus the inaccuracy, right? The 13th problem is that, what are the advantages of adaptive step size in an algorithm for the numerical solution of ODE? As I said, so this would give, this is an essentially, you do a trade-off between these two, but you would use this method so that you can get better, more accurate, that is correct to say, not accurate, more accurate solutions. That is the reason you would be using any adaptive time step. You get better solutions within lesser time, ideally speaking. Yeah. So that is what you try to achieve with this. 14th question. The following ODE is a simplified model for cell dynamics in the tissue. X is the number of cells, P and Q are the rate constant for cell division and cell death respectively. So dx by dt is given by px minus qx square. What will be the value of x after a very long time? Consider the initial number of cells to be x naught greater than 0. Again, after a very long time, as we have done previously, x dx by dt we consider it to be 0, since after a very long time, or at the steady state, which this is what we call steady state, after a very long time, or uh, at t goes to infinity, right? Then the system is considered to not have any perturbations or changes. So we take this dx by dt equals 0. So taking that, what we get, px minus qx square equal to 0, which implies x equal to 0 or x equals p by q, right? So these two are the possible solutions for this. So let's say as x equal to 0, what does that mean? That is the x, which is the number of cells, is essentially 0. So that is at steady state, that is possible when there is completely no cells. But if you look at how this starts, that kind of state is possible only when here, since it's not px minus qx, it's px minus qx square, we have different order of cell growth and cell death. So it is possible if you start with initially no cells. That is to say, it's a trivial case where there is do not have any cells in the system to begin with. So there is no cells at all, even the at t equal to infinity. So the solution which you would consider here is x equal to p by q. Since even if there is x is greater than 0, x naught is greater than 0, it would behave in a different fashion, giving a steady state of x equal to p by q, right? 15th question. For the following ODE, calculate the value of y at time t equal to 3. At t equal to 0, y equal to 1, that is y naught equal to 1. T equal to 3, we need to calculate y. So y dy by dt is given as 1 minus e power minus t. So this is kind of straightforward to, I mean, it's easier to solve it directly. So we have integral, we can integrate on both sides. So we have integral dy equal to integral 1 minus e power minus t dt. So this would be, then we have y, and we are integrating from limits. So we have 0 to 3, integral 0 to 3. Integral dy is y, as we have seen before, and integral 1 dt, integral 0 to 3 1 dt minus integral e power minus t dt, again 0 to 3, right? Which implies we would have y of 3, which we need to find, minus y naught 1, which is equal to t 3 minus 0 minus, or I'd say plus e power minus t 0 to 3. This is what you would get as the answer. So y of 3 would be 1 plus 3 plus e power minus 3 minus e power 0 is 1. So you would have y of 3 equals to 3 plus e power minus 3. It should be as given in solution. I think it's 3.049 is what's given, but yeah, around it comes to be the same value, right? So coming to 16th question, we are growing fish in a tank. We want to model the population dynamics of the fish using an ODE based model. The space in the tank limits the growth, so we use a logistic growth model. Fishes are harvested for selling at a rate independent of the population of fish in a tank. Which of the following is the correct model for the system? X is number of fish. So first they have, let's say the x, it is x, right? So dx by dt is what we are trying to model. So we have two terms. So this would be uh, production rate of the fish, or this will be degradation rate. It can be the whatever terms you can use, but it's essentially a growth rate of the fish and the decay rate of the fish or the death rate of the fish here. So this here is logistic growth is what is given, and the space in the tank limits the growth. So if we used, if you remember the logistic, what do you say, equation for this, it would this is of the form 1 minus x by k, right? K is a carrying capacity of the of the environment, and P is another constant. So you can go through the lecture for detailed descriptions of the logistic growth models and model. So as such, this is the production. Production is given as a logistic growth. So this is what you would consider. Degradation, he says that fishes are harvested for selling at a rate independent of the population of fish. So it's completely independent of the population of fish. So it would be some constant which they have defined as, let's say, some q. So it would essentially be dx by dt equal to px into 1 minus x by k minus q, which would be our option C, right? Okay, so I think we are done with the additional practice problems for this first session. I'm still around for a few more minutes. You can ask me if there are any doubts. You can ask on your chat or chat box, wherever. If not, again, we'll meet next week. So I'll just stay around for a while. You can leave. I'll share this. I'll share the PDF of this whatever I've written, as well as this video which I've been recording, and then it will be posted on the group as an announcement or with the link, or you'll be communicated about it. So don't worry about that. You'll get these resources. But yeah, I'm still around. You can ask me any doubts if you have. If not, have a good night.
Sir, I have a doubt regarding class.
Yeah, please go on.
Sir, first I have to share my screen.
Regarding class and things, not what we have discussed today, or is it something else?
No, sir, what Biplab sir have taught. I have made the graph and sir, I have some confusion regarding that.
Okay, okay, okay. If then can you just wait for a while? We'll discuss that at the end. So if anyone has any doubts regarding the session right now, I would like to clear that first and then stop the recording, and then you
Yes,
can ask me.
sure, sir, sure, sir.
Okay, then if we do not have any other doubts, I'll stop the recording. So I just wanted to see if, I mean, that's okay. So if I'll stop the recording, and then we can, I'll end the session.